Hello, this is Ritvik Ganguly and welcome to my CS343 Operating Systems Assignment, Segmentation and Paging in Linux. Let us first look at the objectives of this assignment. We'll have a brief review of the memory accesses in operating systems. We'll then look at the types of memory addresses available to us. Then we'll go through the concept of segmentation and paging. After that, we'll delve deep into the study of segmentation and paging in Linux environment. Then at the end, we'll have a study about how we can boost performance of paging. And then at the end, we'll see a comparative study of segmentation and paging, and we'll see which one performs better and which one will be suited more to Linux environments. First of all, a review of the memory accesses. So as we know, the main memory in computer systems is RAM, but it always has a limited memory storage. More often than not in today's modern systems, it's 4 GB, 8 GB, or in some cases 16 GB. But some processes might require more than that. Sometimes more than one processes take place at the same time. So if we try to give all the processes a place on the main memory and that is in the RAM, it would not fit always. It would give memory exceeded error. So what we need to do is we have a virtual memory in place where when the process actually requires it, we'll just map the required memory onto the main physical memory, and that way we can have as much memory access as possible, which is much more than the 4 GB or 8 GB of the RAM which we are allotted. So let's take a look at the memory addresses. There are three types of memory addresses in computer systems, that is logical address, linear address, and physical address. Is unit known as the memory management unit, or the MMU, is in charge of transforming the logical address into a linear address, and after that a linear address into physical address. The main parts of those units are the segmentation units actually transform the logical, or transform, or in better sense of a word, map the logical address into a linear address, and then a paging unit actually maps the linear address into the physical address. What we see in logical address is the machine language instructions that are required to specify the address of an operation or of an instruction. Then coming to the linear or the virtual address, it's just a single 32-bit unsigned integer that can be used to address up to 4 GB memory. And at the end, we have the physical address, which are actually the memory cells in the memory chips. They actually correspond to the physical electrical signals sent along the address pins of the microprocessor. They are represented as maybe 32-bit or 36-bit unsigned integers. Now that we have an idea about the three types of memory addresses, let us see what the concepts of segmentation and paging actually are. So in segmentation, a process is divided into chunks of memory called segments. The chunks that a program is divided into does not necessarily need to be of the same size. So where does segmentation come into play? When we have a large process but we don't have that much memory in the physical address space in a contiguous way. So what we do is divide the process into various segments and then allocate the segments to the physical address space. That is what a segment table does, and the process is called segmentation. There are some advantages and disadvantages of segmentation, as we can see here. In segmentation, there is no internal fragmentation because the memories that are mapped to the physical address space, they are just as much as it is required. There are no fixed memory spaces, so it is dynamic, and so there is no chance of internal fragmentation. Also, the segment table consumes much smaller space in memory in comparison to page table in paging, which we'll see later on. One disadvantage of segmentation is that because we are breaking down the process into various segments, there is a chance of external fragmentation, and the free memory space here in the physical address space is also broken down into various non-contiguous memory spaces, which is actually called external fragmentation. So that is a disadvantage. Now let's move ahead to paging. Paging is a memory management scheme that completely eliminates the need for contiguous allocation of physical memory. It actually permits the physical address of a space to be non-contiguous. Till now we have seen the physical address space has to be contiguous, but paging, by implementing paging, this will be removed. This is actually implemented with the help of a page table, as we can see here. A page table basically converts a logical address into a physical address. The logical address is basically divided into various segments called pages, with each of them having a fixed size called the page size. And also we divide the physical address also into segments called the frames. But the one main thing here is the page size needs to be equal to the frame size. We can see there are various types of page tables involved, which optimizes performance. There are the inverted page tables, there are hierarchical page tables, and hashed page tables as well. Now we'll delve deep into what happens in Linux actually. So let us start with segmentation. Linux actually uses segmentation in a very limited way. Why? Because in Linux, the logical addresses actually coincide with the linear address. So there is not much need of mapping the logical address into a linear address. Since the relationship is basically one-to-one, mapping them would not optimize the performance that much. So that's why it's a bit redundant. Usage of segmentation is a bit redundant. Still, Linux version 2.6 and above uses segmentation only when required by the 80 into 86 architecture. So what happens is there are two modes for processes running in Linux: the user mode and the kernel mode. The user mode will have all the processes in the user mode will have two pairs of segment: the user code segment and the user data segment. And in kernel mode also the kernel code segment and the kernel data segment. User mode is basically all the applications that are coming in, the processes and etc. And in kernel mode only the OS handles which are restricted for usage to external users. Okay. So in Linux we have a global descriptor table, or as it is properly known as GDT. In uniprocessor systems there used to be a single GDT, but now in multiprocessor systems, in modern systems, there is one GDT for each CPU. We will see that each GDT actually contains 18 segment descriptors and 14 null, unused or reserved entries. These reserved entries can't be used by normal processors for or segments. So these 18 segment descriptors point to be segments like we've already mentioned, four segments: the user code, the kernel code segment. We also have a task state segment, a segment including the default LDT or local descriptor table. There are three thread local storage segments and three advanced power management segments, which handle basically the power systems, the BIOS services, the multi-threaded processes, like the usage of multiple segments for multi-threaded processes and so on. In kernel, since most Linux user mode applications don't use a LDT, what the kernel does, it defines a default LDT, and that is shared between various segments as well. Now moving on to paging. Now paging is a very important topic in Linux because it helps to optimize the memory accesses in a very good way. So Linux adopts a common paging model for both 32-bit and 64-bit architecture. So whatever code is written, we may have to ensure that they run both on 32-bit and 64-bit architectures. So for, as we can see, the Linux paging model is there on the side. The structure is such that a page global directory PGD will contain multiple page upper directories, which in turn will contain multiple page middle directories, which in turn will actually contain a set of page tables. And at the end, these page tables, each page table will map to the frames for the physical space. So that is it. Each process has its own PGD and its own set of page tables. When a context switch occurs, Linux saves the control register in the segment descriptor of the previous process and loads the same for the next process. This is basically the Linux paging model. Now moving on to the physical memory layout, we can see that during the initialization phase, the kernel builds actually a physical address map. That what it does, it specifies the availability ranges of the physical addresses for use by the kernel. Like not all physical addresses can be used by the processors or by the kernel. There are some reserved page frames that can never be dynamically assigned to, neither swapped to the disk. So that is why it develops a physical address map. The kernel actually builds a physical address map while in the initialization phase. Next, we have the process page tables. It actually is a linear address space for a process and is divided into two parts. We'll see that the addresses from 0x000 to 0xbFFFF can be addressed for both user and kernel mode. Mainly it is used by the user mode, but as you can see in some cases, kernel mode also accesses addresses in this range. But in the next range, that is from 0xC00000 to 0xFFFF, can be addressed only in the kernel mode. User mode processes cannot access these addresses. That is very, very important. There are also some kernel page tables. The Linux kernel actually maintains a set of page tables for its own use and is routed as a master kernel PGD. After the first initialization, this set is never used directly by any process or even by the kernel thread. So that is one time initialization. After that, it will not never be accessed nor can be changed. Next, we have the initialization of the kernel page table. Like here we have learned the kernel maintains a set of page tables for its unit. So how do we initialize them? This is actually a two-phase activity. Right after the kernel image is loaded onto memory, the CPU is still in running mode, real mode, which means that paging is still not enabled. So we have to enable it from the external. The kernel has to externally enable it. So what it does in the first phase, it creates a limited address space, which includes the kernel code, data segments, the initial page tables, the first page tables that we learned in the previous slide, and some memory. That is a very little memory as compared to the RAM which we have in store, around 128 KB. This will actually store the dynamic data structures. This installs the RAM and initializes its code data structures for further usage. And then the kernel uses all of the existing RAM and sets up the remaining page tables properly without problem. Now, at least 128 MB of the linear address are always left available. Like there are some safeguards in place so that the kernel uses them to implement non-contiguous memory allocation. Okay. Next, we'll see how we have learned about how Linux implements paging, but there are some certain ways it can also boost the performance. There are hardware caches and translation look-aside buffers. I'm coming to translation look-aside buffers in the later stage. Let's first see hardware cache. For optimizing cache performance, the kernel actually considers the computer architecture in deciding the following. It will see the most frequently used fields of a data structure, and also will check when allocating a large set of data structures, the kernel tries to store each of them in memory in such a way that all the cache lines are used uniformly. Instead of a cache line storing all the data, we are uniformly distributing them among all the cache lines. Now coming to translation look-aside buffers, or TLB. TLB is basically a fast working cache which optimizes the need for mapping. Like instead of mapping every time allocation comes, we'll have a fast working cache in store which will contain the most frequently used mappings. If the mapping is not there, then we'll check the normal way, and that is called a TLB miss. So what Linux 2.6 Plus offers for reducing these TLB misses is that it adopts a technique called, the kernel adopts a technique called the lazy TLB mode. It actually avoids useless TLB flushing, thus reducing the TLB misses. Now at the end, let us compare the segmentation and paging. In the beginning, I have told that Linux uses segmentation in a redundant way. Not much application is there, but we have seen paging. In paging, the Linux adopts many functionalities. So why does Linux prefer paging to segmentation? We see various reasons. We see the memory management becomes simpler when all processes use the same segment register values instead of the process dividing itself into segments. That is when they share the same set of virtual addresses. Next is one of the this is very important. One of the design objectives of Linux is portability to a wide range of architectures. Linux is an open source software, so it tries to cater to a very wide range of architectures that is available on the market. So as we know, since RISC architectures have limited support for segmentation, therefore Linux gives paging precedence, so that the code that is written or Linux runs on all types of computer architectures there is in the market. So that is it. Paging also distinguishes pages from page frames. This actually allows the same page to be stored in a page frame, stored to a disk, and then reloaded in a different page frame. Which is this entire process is the backbone of the virtual memory mechanism, which is used in virtual machines and while gaming and stuff. So that is very important. So that is the end of the study. I've used various references as is available here. So thank you. Hope you have enjoyed this.